Thank you again for joining us today on this webinar for advanced microanalysis for automotive and aerospace materials using wavelength dispersive spectrometry. So I'm Laurie Pallas. I'm the Global Application Manager for the Electron Microscope Analyzers at Bruker Nano in Berlin, and I will be the host for this webinar. And our presenter today is my colleague, Dr. Michel Abratis. In this webinar, we will review the advanced capabilities of WDS to support the development and quality assurance of materials used for the aerospace and automotive industries. We will explain how WDS is an essential analytical tool when analyzing light and trace elements and complementing the elemental distribution analysis by EDS. And why with a WDS detector with a grazing incidence X-ray optics, we can enable measurements at low prop current to achieve high spatial resolution, which is essential when identifying very fine inclusions that are critical in cellular analysis, for instance. So first, housekeeping details. So you see the webinar title slide on your screen. The webinar is interactive. You can ask your questions anytime using the question and answer window, which is on the right side of your screen. The presentation will last about 30 minutes, and after the presentation, we'll move on to the Q&A session. The webinar is recorded and will be available soon for on-demand version. So first, let me introduce our presenter, Michel Abratis. Michel studied geology at the universities of Kiel and Göttingen in Germany, where he also received his PhD. During his academic career, he focused on analytical geochemistry using mass spectrometers and microprobes to analyze rocks and their minerals. And Michel set up and managed a microprobe lab at Jena University before joining Bruker Nano as a senior application scientist 10 years ago. So the presentation today is divided in 3 parts. So Michel will first review the WDS technique and the advantages of the parallel beam optic approach with grazing incidence. He will then present application examples for the automotive industry, looking at ceramic used in the catalyst and permanent magnets for electrical engines. And in the third part, Michel will delve into titanium and nickel-based alloys for turbine blades and discussing the inclusions. So now I will pass the presentation to Michel. We'll start.
Okay, thank you very much, Laurie, for the introduction, and hello everyone in the audience. WDS is an essential microanalytical technique offering remarkable precision and accuracy in elemental analysis. Its role is crucial in the development of high-performance materials within the aerospace and automotive industry. These sectors demand exceptional material quality, durability, and performance, making WDS an indispensable tool in ensuring these standards. The Bruker WDS is a special type of WDS with an optic that provides a parallel X-ray beam. Before I present some applications, I will give you a brief introduction into the technology and its characteristics. Bruker offers several analyzers for SEM which work together very well. The QUANTAX WDS is best operated in combination with the QUANTAX EDS. I will present a sketch here to illustrate the technical characteristics of the 2 detectors. Here's a sample. An electron beam from the SEM hits the sample and generates X-rays. These X-rays can be captured by an EDS, which analyzes and counts the photons in a single process. The WDS here on the right side consists of 3 main parts and splits the analysis and counting of photons into 2 separate steps. A parallel beam parallel beam optic transforms the X-rays diverging from the sample into a parallel beam that hits the diffracting crystals. Bragg diffraction takes place at one of the 5 or 6 analyzer crystals on the turret. The respective measurement energy is determined by Bragg angle theta and the crystal lattice constant of the respective analyzer crystal. The X-ray detection or counting is then done in a flow proportional counter. Benefit of such a WDS with a parallel beam optic is the large solid angle and thus high sensitivity for low energy X-rays. QUANTAX WDS is fully integrated in the Bruker S3 analysis software. On the top right, you see the configurator for WDS. EDS and WDS acquire the X-rays simultaneously, and the resulting data can be combined. Here you see a spectrum. It's a point analysis on a sample, and this is the spectrum with the EDS data and the WDS data. Here, a 3-point measurement with peak counts and counts on the background to either side of the peak. Remember that WDS is energy selective, so measuring one energy after the other. And this can also be seen in a video here that demonstrates how the WDS operates. We will see mapping in this video. Let me start the video. We start by capturing an image on the sample. So here's the WDS configurator. We capture an image of the sample. After having defined the element in X-ray line of interest, we launch the mapping process. We press acquire, and the X-ray energy for beryllium K alpha in this case is adjusted and mapping starts off. So it's mapping of the energy of beryllium K alpha at 109 electron volts. And when that is finished, the next energy, which will be carbon, is mapped. So now there's a second capturing process for the energy of 277 electron volts for carbon is adjusted, and this energy is measured. At the same time, the EDS is continuously measuring and showing more elements at the same time. Finally, combined WDS and EDS mapping is finished according to the predefined acquisition time of 1 minute for each of the 2 elements. Yeah, so this is how EDS and WDS is combined, and this is to show that the measurement for WDS is energy selective and sequential. Okay, well understood. WDS is energy selective. Measurement will thus take more time. So what is the advantage of WDS? The answer is shown here with the properties. First of all, on the left side, spectral resolution. The measure is the full width at half peak maximum, or simply the peak width. At the given energy range between 100 electron volts and 4 keV, we see the performance of the EDS in black. The half width ranges between 50 electron volts and 100 electron volts. And down here with the colors, we see the performance of the WDS. So much narrower peaks, lower half width. For the WDS, we see 5 different colors, and that is due to the 5 different analyzer crystals. The ability to detect trace elements is determined by the detection limit. Due to the higher signal noise ratios for WDS, the detection limits for WDS are much lower than for EDS, especially in the low energy X-rays or in the low X-ray energy range. Let's summarize the characteristics of QUANTAX WDS and EDS. Both detectors acquire the X-rays simultaneously, and the resulting data can be combined. Therefore, you can profit from the specific advantages of both systems. EDS is very fast. It allows simultaneous detection of all the energies present in the sample, and it can also operate at low beam current. WDS, on the other hand, shows much higher spectral resolution, up to 20 times higher. It shows much higher peak to background signals, so we get to much lower limits of detection. We can analyze trace elements better. And third plus is the outstanding sensitivity for low X-ray energies. So the limitation is the energy range and the sequential measurement. Therefore, both systems have their advantages, and the best is combination. So WDS is an ideal technique to complement the EDS in demanding applications, as for example, applications in the automotive field of industry. So now we will have a look on some of these applications. The automotive industry is highly innovative and of great importance for the global value chain. Even though Germany is only fourth now in the ranking of car manufacturers, the industry sector still accounts for 4 to 5% of GDP in Germany. In automotive industry, WDS contributes significantly to the analysis of welding processes, exhaust gas catalytic converters, and shield metals and alloys. It assures the quality and reliability of materials used in vehicle bodies and engine components, ultimately enhancing the safety and performance of automobiles. Car exhaust fumes from combustion engines are a burden to the environment and a threat to the health. These problems increase dramatically with increasing mobility, and therefore catalytic converters were introduced 40 years ago in Germany, and probably more or less at the same time elsewhere as well. The catalytic converters transform harmful pollutants into safer compounds. Here's a catalytic converter shown and its effect. A catalytic converter consists of a porous ceramic body with a cellular structure, which is coated with a highly granular material that contains traces of precious metals such as platinum or rhodium, and provides a 5,000 times increased contact surface for flushing the exhaust gases. The effect of the catalyst is oxidation of carbon monoxide to carbon dioxide and reduction of nitrogen oxides to nitrogen. And with this, the catalytic converter can decrease the NOx load by about 80 to 90%, and the carbon monoxide load by even 90 to 98%. The analytical questions here for us are, can we detect platinum in trace levels within this material? And also, what other elements can be detected for failure analysis? Let's have a look on the catalytic converter. Here we see the grid or the in cross section, so the ceramic body. We zoom in here. Each of the cells is about 1.5 millimeter wide, and we get a quick overview by WDS mapping. The ceramic grid is shown in bluish colors. It consists of aluminum, silicon, magnesium, and oxygen, clearly not shown. And the active surface is shown here in these orange colors. This active surface is made up mostly of titanium and tungsten. This can be seen also in the spectrum of this material. Here we see titanium, tungsten, and oxygen. So titanium and tungsten oxides. So, but where is the platinum? So we cannot see the platinum right now. Therefore, we zoom into the sample on the outlined rectangle. We zoom further in and we see the very granular porous material, particles of different size, a very high surface of it's very porous, this material. We further zoom in and we see that even the larger particles consist of smaller particles. It's a heterogeneous mass with some bright particles and darker matrix. The particles are less than a micrometer in size. So we know that the acceleration voltage is of importance. We have to confine the acceleration voltage to decrease the interaction volume. From the equation of Anderson and Hassler, 84, or Monte Carlo modeling, we can estimate the interaction volume. So by 20 kV, using 20 kV, we have an interaction volume of 2 micrometer, which is too large to separately analyze the small particles. We have to reduce the acceleration voltage to about 5 kV. And here we see spectra from acquired at 5 kV from the different particles, the bright and the darker areas, and we see differences, especially in the content of tungsten and also in the content of titanium. So the brighter particles contain more of the heavy element tungsten. Now the question is it really tungsten or is there more at this area? So we have the great tool of EDS deconvolution. So the EDS is limited in spectral resolution, but has this tool of spectral deconvolution that helps in many cases to sort out the overlaps and well define the energies. So tungsten fits very well, but minor contents of silicon and tantalum may also be possible in this energy region. They're exactly at this position. Then we have an indication for zirconium, but at the same position, there's also platinum. So we have to sort this out, and using 5 kV, it's difficult. Using higher kV, we would see a high energy line of the platinum around 9 kV, but we are limited to low kV because of the spatial resolution. And then at about 2.3 kV, there is a peak marked as lead, which does not fit very well. It could also be molybdenum or sulfur. So we see that here. Platinum fits also well, sulfur fits well. So what at the end is it? And we can solve this question by using the WDS, which is shown on the right side. We can scan, make an energy range scan across this defined area, and we can well see the peaks for platinum, the M alpha peak and the M beta peak for platinum. And there is no zircon at this position here. So we confirm platinum and can exclude the zircon. And the same we can do for the tungsten. We can do a WDS range scan across this energy range, and we confirm the presence of tungsten, rule out any tantalum and any silicon in this sample. There is in some, so due to the ceramic grid, there may be some silicon, but in the pure particles, there isn't. And further scans across this range here, showing again the platinum. We also find other traces such as niobium. So little contents of niobium. Here's the L-alpha line, and the L-beta line is present as well. We find sulfur. Maybe I forgot to tell you, this was a used catalytic converter. So sulfur may be from the exhaust gases. So there's clear evidence for sulfur, and there is no evidence for any lead or any molybdenum. So that's it for the catalytic converters, and we move on to more modern vehicles. And this is now on electric cars. We continue with electric motors, and for these we will have a look on permanent magnets. So a substantial expansion for electromobility is necessary for the energy transition and the achievement of climate targets. High performance electric motors rely on the use of permanent magnets, which are more efficient than electromagnets. They also require less maintenance and allow for a more compact motor design. And as I said, we need permanent magnets. The most powerful permanent magnets contain rare earth elements such as neodymium. The rare earth elements are critical elements, and probably you did not miss that the rare earth elements are very popular these days in global politics. And since we cannot, or since not all countries have reserves and not all politicians want to make deals with Ukraine, we have to focus on alternative sources for the rare earth elements. And there is recycling of used magnets and other RE-containing waste. And this is what my colleague or our customer and collaborator, Eric Robin from the CEA Research Institute in Grenoble, France, did. Here I present his data that he has already shown in a preceding webinar also, where he showed these together with more WDS data that he acquired. His intention was to characterize the RE-rich phases that formed in a metallic melt as a first step towards efficient recycling processes. This micrograph here on the left side is of a sample that contains ferrite with inclusions of 2 to 3 different rare earth element-rich phases. So there are the red phases, 2 reddish phases, and the greenish phases. As you can see, the inclusions are very small, so less than a micrometer, a few hundred nanometers only. And the challenge here is discrete analysis of these phases. Here is a part of an EDS spectrum of these samples. The metal scale lines and the REL lines of interest are in the energy range of about 5 to 8 kiloelectron volts. Efficient excitation of these X-ray lines requires at least 15 kV acceleration voltage. And with 15 kV or more acceleration voltage, we end up at large interaction volumes. So here again is a modeling according to Anderson-Hessler, and we see with 15 kV we end up at 600 nanometer, with 20 at 1,300 nanometers. So this is much larger than the size of the small inclusions. So we would include the matrix in the analysis, which is clearly bad. So we have to lower down the acceleration voltage And here we see the results of the modeling of the interaction volume with 5 kV application. We have an interaction volume of only 125 nanometers, which is very suitable for analysis of the inclusions. So applying 5 kV is shown here, and we see the EDS spectrum of one of the phases. Now we struggle with severe overlaps, even more overlaps than with the airlines we have here now with the rare earth element M lines. So there's overlap of neodymium, praseodymium, and so on. There's overlap of the cobalt and iron in this phase. So difficult to determine. It's much easier to analyze the samples with WDS because of the high spectral resolution. Here we have a lot energy lines, and we can find separate lines for the iron, for the cobalt, for the praseodymium, neodymium, for the dysprosium, and analysis is much more reliable, and we get to better data, better sums, and better ratios of the composition of the rare earth elements and the metals, and we can also well determine the boron content. So here the WDS is of advantage. We have a separate dysprosium-rich phase, and the same is valid here. WDS has a higher spectral resolution and gives at the end better results for these complicated analysis. Yeah? So the advantage is the resolution of the rare earth element and also the sensitivity for boron. And so we end up with some better data. And now we have a look also on the third phase here, the green phase, the neodymium-rich phase, and there's a lot overlap between iron L lines, cobalt L lines, the rare earth elements of praseodymium, neodymium, a lot overlaps. We use in this case a slightly higher acceleration voltage to have a higher signal. This is something we can afford here with the larger phase, 10 kV. And yeah, with EDS, we have yeah, larger deviation because it's too complicated to sort out, to deconvolve. The overlaps, the sums are deviating from 100%, and the results are more precise, more accurate with the WDS, where we can separate the single peaks and get to a better composition in this case here also. So that's it on automotive samples for today. And we continue with applications for aerospace materials. The aerospace industry has a high demand for exceptional material quality, durability, and performance, since their products components have to withstand extreme physical conditions. During usage, the role of WDS is crucial for the development of high performance materials, quality control, and failure analysis here. And yeah, so we first have a look on turbines, turbine blades. As you see here to the right side, there's an opened up turbine jet engine with the turbine blades, and some of these blades we used for analysis. Here we have received 2 blades which were said to be from the same jet engine. One is a titanium-based alloy and one is a nickel-based alloy. They are quite small, about 2.5 centimeter long, and this about 2 centimeter. And we prepared the sample. We have a look first at the titanium alloy turbine blade. This shows a granular structure. So the grains are surrounded by bright, high density phase in the interstices. We zoom in here and see the gray titanium alloy grains surrounded by a very bright high density phase at the interstices. And if you wonder about the speckles here, this is related to sample preparation. So it's some organic matter. What is challenging is are the interstices. They are very fine, very small, about 100 nanometer. And you really have to search for areas where it's somewhat thicker. So once again, we have to reduce the acceleration voltage by reducing the or reduce the interaction volume by reducing the acceleration voltage. So if possible, we go down to 5 kV again to selectively analyze the interstices in this sample. The grains are composed, we see here an EDS spectrum, the grains are composed of titanium alloy containing aluminum, zircon, some tin. And the interstices, they contain more zirconium and some molybdenum. This is at least what the EDS tells us. Here are the spectra once again. And yeah, the question is, once again, molybdenum, there's also sulfur and lead. Are there some traces of sulfur and lead that we can find in the sample? And is the zircon really zircon, or is it platinum like we had it in the catalyst? So we are using the marvelous EDS deconvolution, and it seems zircon fits quite well, and the molybdenum also. But also platinum would fit well, and we cannot decide if there are traces of silicon or, traces of sulfur and lead. So to confirm or to reject, we are using the WDS. We perform energy range scans across the area of the zircon, and we confirm the presence of zircon that clearly matches. And we can confirm that both in the grains and in the interstices. And in the interstices, we can also confirm the presence of molybdenum. Other elements such as platinum don't fit, and also the presence of sulfur and lead can be ruled out. What WDS can find also are some traces here. In this case, it's silicon, 0.02% or 200 ppm and 400 ppm of silicon were found in these analysis. So WDS shows once again its advantages for spectral resolution and also for trace element analysis. So in EDS, the silicon hides behind a peak of zircon here in this energy region. Yeah, and now that we can well trust the identification of zircon and molybdenum, we can acquire nice mapping here by EDS, also on the right side, showing the grains are rich in aluminum and titanium in pinkish color, and showing the interstices, which are rich in zirconium and molybdenum in this light green color. We go on with the next type of turbine blades, the nickel alloy-based blades, and these consist, as we see here, of large grains of titanium alloy, so up to 100 micrometer in size. So it's mostly nickel, but containing also chromium and aluminum. And with EDS deconvolution, we can also easily find some portions of cobalt and of titanium. So the overall composition is shown here, mostly
nickel, but then also high contents of chromium, cobalt, some titanium, and some aluminum. What is more interesting than the nickel alloy grains are the inclusions in these samples. And we see here some obvious inclusions, the bright inclusions in the area, and some darker inclusions, and also some very tiny inclusions on the borders of the grains. So we have three types of inclusions. EDS can already tell us the main components. So we have zircon carbide inclusions, we have titanium carbide inclusions here, and we have trails of chromium carbides. The zircon carbide inclusions are associated with some corrosion. So this may be a challenge or problem for the turbines, and we have to find out what creates the corrosion. When we do the analysis of these inclusions separately with low kV to confine the beam inside the area, we find sulfur besides zircon and carbon. So we can clearly see that in the EDS spectrum by deconvolution already, and we can confirm it by WDS. With the range scan here, we can rule out any molybdenum or lead. And we can further investigate these inclusions for trace elements, and we find here selenium, 0.1% in the sample, and some traces of aluminum, 0.05%. So this can nicely be shown by the WDS. And at the low energies, we can also find some contents of boron. So there is a portion of boron inside these samples, which is overlapping with the zirconium and zeta lines. And since it is overlapping and the intensities are quite low for the EDS, it cannot be found by the EDS, but only by WDS. We have a look on the second type of inclusions, titanium carbides. And here, so besides titanium and carbon, they contain some minor elements which strongly overlap. And with WDS, we can easily find tantalum and tungsten also, which was not indicated. We can rule out the silicon. We can find the zircon and niobium. So all in the lower percentage range, or the tungsten even below 1%. And these finally look on the very tiny inclusion trails on the grain boundaries. We applied 5 kV here, and still this is not sufficient. We have a high signal from the surrounding matrix containing nickel and cobalt, but we can clearly see this peak here, which is boron. So they are also borides, and there are traces of sulfur as well in these samples. And I mentioned boron several times, so therefore we can also show that boron we can show some nice mappings here. As I said, WDS and EDS can well be combined. So major elements were mapped here by EDS, nickel, titanium, chromium, zircon mapped by EDS, and boron mapped by WDS. And this is a combined map. It shows all three types of inclusions. The zircon carbides, here in red and blue, the titanium carbides, high in titanium. And here in these orange colors, the tiny inclusions of chromium carbide with some boron contents. And here these show up, the chromium carbides with boron show up in these violet colors. So it's a mixture between chromium and boron colors. And this is a zircon inclusion shown zircon and boron. And with this, I want to summarize. So WDS is an essential, or the combination of EDS and WDS is an essential solution for advanced material science applications. We can achieve high spectral resolution with the WDS and resolve EDS peak overlaps. We use peak resolution instead of deconvolution. The usage of WDS enables light and trace element analysis. And we get down to low detection limits also for the light elements and find traces of a few hundred ppm or even less. And what is shown here as well, WDS application at high spatial resolution is possible. We can operate at low kV and low beam currents, fairly low beam currents. And with that, I would like to conclude.